VLSos, this is a video lesson on reflecting a function, which is a type of transformation. I'm going to draw a sketch of a very simple function to get a visualization of what it means to reflect. I'm going to start with the parent parabola, and what we mean by reflecting is a transformation where we reflect it over a line, much like the line representing a mirror, and then we would see the image beyond it. So reflection is done over a line, and we need to define the line that we're going to reflect over, because where the line is then changes the kind of reflection that you would get. To do a simple reflection, we're going to reflect over the x-axis at first. This would be called an x-axis reflection. We can reflect over any line, anywhere on a graph, but choosing the axes is the simplest way to accomplish the math. So what does that look like? We can simulate a reflection with a piece of tracing paper. In this case, we would start with tracing the function that we wanted to reflect, and then a fold would be simulating the line of reflection. So if I fold this over, or create the fold on the x-axis, then after I fold over what's above, I can see where it goes after the reflection. And I can sketch the result as a lighter or dotted line. This parabola has been reflected across the x-axis. How would I do that with the equation, or how would I do that mathematically or algebraically? In general, we can start with y equals f of x, where f can be any function, and in this case we're using the x squared function, the parent quadratic, graphs the parent parabola. So how do I accomplish an x-axis reflection with a function? There's a counterintuitive thought. To reflect over the x-axis, I make y negative. In general, if I make y negative, it will make the x-axis reflection. And in this equation, whose graph is here, I make y negative simply like that. And I have created the equation for this dotted line, the reflection. Now we are used to, and in the habit of solving for y, we don't need to, but if we did, it would look like that. Y is equal to negative x squared. Okay, we could reflect across the y-axis as well. And for that, we'll create another graph. In this case, I'm going to choose an exponential function to start. I can get a visual by using tracing paper, tracing the function that I'm going to reflect, and then folding it along the line that I'm going to reflect the function across. And in this case, I want to show you a y-axis reflection. So if I fold, we have the function represented on both sides of the line of reflection. That's okay. If I fold across, if I make a fold at the y-axis, I can see that this part of the function is going to reflect here. And at the same time, on the right, it's going to reflect to the left. So if I do both of these at the same time, the reflection will look like this. And I can sketch the result of the reflection as a dotted line. So I have the parent exponential, exponential base 2, and the reflection across the y-axis. How is that done mathematically? What we're talking about is a y-axis reflection. In general, we could use the equation y is equal to f of x to represent all equations, all functions. And there's a counterintuitive thought if I want to reflect across the y-axis, I make x negative. Inside, I would make x negative inside the function. So if this function in this example was y is equal to 2 to the x, exponential base 2, then the reflections equation is making x negative by putting a negative in front of it there. Now, in this case, it would be worth reminding us of a truth algebraically that might catch us or cause some confusion here, and that is the negative of x squared is not equal to the negative of x squared. Notice when I said it, I said the same thing, but it's the parentheses that makes the difference. What's the difference between these two? This is taking the negative after you square x. In the order of operations, we have to do exponents before we multiply. Making something negative is like multiplying by -1. Whereas here on the right side, we take the negative of x first because it's inside parentheses, and then we square it. And we know that if we square a negative, it becomes positive. Whereas here we square x first, still positive, and then we make it negative, and it should be more obvious that negative x squared is not equal to then what becomes positive. Why do we remind us of that? Because in the x-axis reflection where we made y negative, we move the negative over to the other side because we're used to simplifying by solving for y. But in this case, it's not the same as making x negative. This negative x squared is not the same transformation of having made x negative first and then squaring.